Right. Good evening once again. So we are hoping to complete the algorithms today. Yeah. So we got divide and conquer, greedy, graph algorithms, dynamic programming, searching and sorting. We will complete this, man. And we are actually not going to go through the implementation part because I need to be strong at coding. If you kind of click on these things you're going to see some codings. C++ coding. All right. Java, Python. There is C sharp and JavaScript. So I'm thinking of doing it in Python someday or the other. I will do it. And you don't need any libraries to do that as well. So divide and conquer is an algorithmic paradigm in which the problem is solved using the divide and conquer and combined strategy. A typical divide and conquer algorithm solves a problem using following three steps. Divide. This involves dividing the problem into smaller subproblems. Conquer solves subproblems by calling recursively until solved. Combine. Combine the subproblems to get the final solution of the whole problem. Below are different algorithms which are based on divide and conquer, applications of divide and conquer in binary search. Binary search is a search algorithm that efficiently finds a target value within a sorted array. It repeatedly divides the search space in half until the target is found or that search space is empty. Algorithm steps initialize low, high, and mid indices. Compare the target with the element at the mid index. If target is found, return the index. If target is smaller, update the high value to mid minus 1. If target is larger, update the low index to mid plus 1. Okay. Repeat the process until the target is found or the search space is empty. Application of divide and conquer in merge sort. Merge sort is a divide and conquer sorting algorithm that recursively divides an array into two halves, sorts each half, and then merges them to provide a sorted array. Divide the unsorted array into two halves, recursively apply merge sort to each half, merge the sorted halves to produce a sorted array. The worst case, average case, and best case time complexity is O of log n because the procedure is independent of the elements. Space complexity often adds additional space for the temporary array used in the merge step. Okay, so alright. Technically, it is the auxiliary space because we have studied the technically speaking, it is the auxiliary space because space complexity is the space taken by the input plus the auxiliary space. Any sorting algorithm needs to store the elements, so the space is O of n by default. But merge sort needs additional space for combination, so that is different. And what would be the total time complexity in this analysis? Space complexity and auxiliary space, alright. Okay, just the n value is different. Recursion stack. Input array unavoidable for any sorting algorithm. Temporary array used during merging. Recursion stack. Okay, makes sense. Now here is a thought to push deeper. Quicksort has that same time complexity on an average auxiliary space. Okay, even though the space complexity is n, the n value is different for insertion and merge sort, for instance, because even though it's linear, the n value is higher for merge sort for the same input in comparison with insertion sort. Even though both insertion sort and merge sort have linear space complexity in terms of input array, the effective or practical space usage differs because of how each algorithm handles the input. Mhm, mhm. In practical, this means that for the same input of size, merge sort consumes more total memory than insertion sort, even though both are technically often. That's why our intuition is right. The linear term hides the fact that merge sort constant factors. Okay, hides the fact that merge sort's constant factors are much larger. Okay, we are understanding and moving forward, which is an important thing. Application of divide and conquer in quicksort. Quicksort is a sorting algorithm based on the divide and conquer algorithm that picks an element as a pivot and partitions the given array around the picked pivot by placing the pivot in its correct position in the sorted array. This key process of quicksort is the key process in a quicksort is a partition, the target partition. The target of partition is to place the pivot. Any element can be chosen to be a pivot and its correct position in the sorted array and put all smaller elements on the left of the pivot and the greater elements to the right of the pivot. Partition is done recursively on each side of the pivot after the pivot is placed in its correct position, and this finally sorts the array. There are many different choices of picking pivots. Always pick the first element, always pick the last element, pick a random element, pick the middle. Alright. Time complexity worst case often square occurs when the pivot selection consistently results in unbalanced partitions. Occurs when the pivot selection consistently results in balanced partitions. Right. Overflow again for the recursive call stack. Now, is it correct for quick sort? Because in theory, the space complexity of every sorting algorithm is often in the very least because you need to store the input size. So there is no way it is overflowing. Maybe he is referring to auxiliary space. I still think the space complexity will be open for this. Even though the core idea is correct, and it is just a misunderstanding of terminology. We still need to be aware of the difference, right? That makes things more clear and interesting. Nuance, what does nuance mean? A subtle difference. Okay, okay, my guy. That is a long discussion. So we will just see how the question patterns are. We will not try to solve all of this. Merge sort can be adapted for linked list. It follows the same divide and conquer approach, dividing the linked list into two halves, recursively sorting each half and then merging it. How to make merge sort to perform more in comparisons. Best case, optimizing merge sort, detecting if the input is already sorted and skipping unnecessary merge steps. Okay. Iterative quicksort. An iterative version of quicksort uses a stack to eliminate the need of recursion. It follows the same steps as the recursive version but utilizes a stack data structure, creates an empty stack and puts the initial values into it, perform iterations until the stack is empty, copy values from the stack partition and puts the indices of the subarray. Okay, because recursion uses memory size. Quicksort on single linked list. Adapting quicksort for single linked list involves partitioning the list based on a pivot similar to the array version. Select a pivot from the list, partition the list around the pivot, recursively apply quicksort. Median of two sorted arrays. Finding the median of two sorted arrays involves merging the arrays and finding the middle element. Okay. Count inversions in an array using merge sort. Counting inversions in an array involves determining the number of pairs of indices I is less than j and array of I is greater than array of j. Okay, these are like DSL equal level problems. Closest pair of points. The closest pair of points problem involves finding the pair of points with the smallest Euclidean distance among a set of points. Sort the points by their x coordinates. Recursively find the closest pairs in the left and right halves. Check for a closer path that spans the two halves. Strassen's matrix multiplication is a divide and conquer algorithm for multiplying matrices more efficiently than the standard method. Split the input matrices into submatrices, recursively compute seven products, combine the products to form the result. Sort a neatly sorted or k-sorted array. Sorting a neatly sorted array involves efficiently sorting an array where each element is at most k positions away from its final sorted position. Okay. Search in an almost sorted array. Searching in an almost sorted array involves finding the position of the element in array where each element is at most k positions away from its final position. Is a modified binary search to find the element. Compare the element with adjacent elements within the range of k. Nice. I don't even know problems like these actually exist. Kth element of two sorted arrays. Finding the kth element in two sorted arrays involves comparing the medians of two arrays and eliminating half of the elements. Kth smallest or largest element in an total array. Find the get smallest or largest element in an total array using quick select. So I need to grind DSA as well. We got greedy techniques. Okay, okay. Yeah. So should we read greedy? Yeah, I guess we should read greedy. Mhm. We got theory of computation. And what is this? Turing machine and undecidability. Compiler design. DBMS. Computer networks. Yeah, this is a big one. Operating systems. Digital logic and design. Computer organization and architecture. Okay. Yeah, obviously this is a big resource. Yeah. The dynamic landscape of algorithmic design, greedy algorithms stand out as a powerful tools for solving optimization problems. Aspirants preparing for the GATE exam 2024 are poised to encounter a range of questions that test their understanding of greedy algorithms. These notes aim to provide a concise and insightful overview unraveling the principles of applications of greedy algorithms that are likely to be scrutinized in the upcoming GATE examination. Greedy algorithm is an algorithmic paradigm that builds up a solution piece by piece, always choosing the next piece that offers the most obvious and immediate benefit. So the problems we're choosing locally optimal and also the global optimal solution are the best fit for greedy. Yeah, No, no, no. Okay. All right. We will do it. How to close this? Okay. Ah, yeah. Okay. DP is having 56 problems. It is standing at the top of the pinnacle. All right. selection sort. Okay, so we will be implementing selection sort. Oh my god. To implement wait, yeah. So first you need to take an array. Okay. Array 1. Let's take a list, right? 20, 30, 50, 10, 15. So what you do for selection sort? You select the smallest element and you swap it. So for I in range len array 1, what you do? Mm-hmm. Okay. Oh god. Alright, I will not look at the code how to implement selection sort algorithm. Divide the list into two parts. Okay, sorted. Minimum element in the unsorted section. Swap it with the first element in the unsorted section. I don't want to look at the code. So you will, alright. To implement selection sort. Array 1 student 20 1 to 45 52. Let's do this. And okay, n is initially set to 0 for I in range len of array 1. Alright, what will you do in this range? So you will check the smallest element. Right. Oh my god. You will check the smallest element and you will swap. So you will do this for every element. For j in range none of r1 minus sorted, sorry, minus n Big is equals to array 1 of 0 if mhm, array 1 of j is greater than big. Big is equals to array 1 of j. So now you got the big element, and now temp is equals to big. Big is equals to you are swapping a big element. Oh my god. Small. Here, let's write small. Small is equals to array 1 of I. Array 1 of I is equals to temp. You swapped them, and now what you are supposed to do? And do we have plus plus? No. Plus 1 is equals to 1. I don't think it is going to work. Print array 1. Uh, Okay. So where did things go wrong? So you are not updating the small element or what? Okay, wait. Okay. So this is out of the loop. Maybe you assume in here small is equals to array 1 of n. Okay, that did something. I don't know what it did. Okay, I guess it's time to ask ChatGPT. We have tried what we could. Wait, what happened? Control A, Control C. What's wrong with this one? Assume array is smallest. Search the rest of array I plus 1 to n. Find index of smallest element. This using index. Okay, it is doing something. Okay. Alright, people, I guess it is high time that I take a break today. Yeah.